right, today we're going to look at some sample questions dealing with rate laws and rate law constants. So here's the first question. You can see there's two different experiments. They've got some different concentrations, and then they give you the rate of the formation of the product. It says the table above shows the results from a rate study of the reaction X plus Y makes Z. Starting with known concentrations of X and Y in experiment 1, the rate of formation Z is measured. If the reaction was first order with respect to X, so let's go ahead and write, because this probably is going to help you. Let's go ahead and write out the rate law here. The rate is going to equal K times the concentration of X. It's first order with respect to X. So it's X, and then second order with respect to Y. They don't ask you for that, but it might help the problem. The initial rate of formation in formation of Z in experiment 2 would be what? So, if the rate of formation of Z in experiment 1 is R, what's going to happen to R when X goes down by half? Well, certainly, since it's first order, they tell us, if X goes down by half, then the rate's going to go down by half. So simply because of X, this rate here is going to become half of whatever it was before. Okay, but then Y is going to be, Y goes up by double, and therefore the rate, because it's second order for Y, therefore has to go up by a factor of 4. So then we're going to basically take that answer and multiply it by 4. So half of R, and sometimes it's helpful to just make up a pretend number. Let's say the number was 10. Okay, first of all, you've got to take half of 10, which is 5, and then multiply 5 by 4, which is 20. Or simply put the 4 on top. 4 divided by 2 is 2. You're going to have twice as much. That rate of formation is going to be twice as much. I'm not sure why these are here. It just didn't, but the answer is R over 4 and R over 2, which if it was just asking about X, then absolutely. X would make it go down by half. That would be the answer. But then because Y doubles in its second order, that has to be an increase of a factor of 4. And so the correct answer is absolutely D. Okay, question number 2. We've got 4 different trials here. An experiment's conducted to determine the rate law for the reaction. The data table above shows the data collected. Based on the data table, which statement is correct? So let's kind of look at our answers here. Notice that every answer has a different rate law. Okay, every single rate law is different. Okay, which means that if we can figure out the rate law, we're going to know the right answer. So let's see if we can do that. Let's look at trials 1 and 2. In trials 1 and 2, the concentration of A2 doubles. B stays the same. The rate doubles. Therefore, we know that that A is first order. And right away, that's probably going to get rid of some answers. Yep, because in A, they have A as second order. So it can't be A. Could be B, but it also can't be C because they have A as second order. Okay, and then let's try to see if we can figure out B. Here we can see that A is staying the same, B is doubling, and then what is the rate doing? Again, and this is a multiple choice question, so you can't really, but just to kind of help you, like 1 times 10 to the minus 4th is the same as 10 times 10 to the minus 5th. So you're going from 5 times 10 to the minus 5th to 10 times 10 to the minus 5th. With those exponents, it can be a little bit tricky when you're doing that. So I always find it easier to try to get them both back where the exponents are the same. Okay, and then obviously you can see that the rate is also doubling, so therefore B is also first order. So A and B are both first order, so therefore, oops, I went too far there. So therefore the correct answer has to be B, A first order, B first order. Doubling the concentrations of A and B will make it double once because of A2, and then it will double again because of B. So yes, the rate will quadruple overall. Okay, let's look at number 3 here. Again, don't worry about the data table yet. The initial rates of the reaction represented by the equation above were measured for different initial conditions or concentrations based on the data table in the table above. Which of the following is the rate law expression for the reaction and why? So again, do we see any that are the same? No, we don't. So the why part doesn't really matter. We just have to get the right rate law. So let's kind of take a look here. Here, those two are staying the same. Here, it looks like Cl2 is doubling. And when it doubles, it looks like the rate of NOCl formation is also doubling. So therefore, we know that Cl2 is first order. So again, that can get rid of some answers. A is out and C is out. Okay, and then let's see if we can figure out NO here. Let's see, let's look at 1 and 3. Because in 1 and 3, Cl2 staying the same, but NO is doubling. And then what does it do here? Again, like the previous problem, 1.82 times 10 to the minus 4th is the same thing as 18.2 times 10 to the minus 5th. Think about what that means, okay? Think about what does 1.82 times 10 to the minus 4th actually mean? It means 0.000182. Well, 18.2 times 10 to the minus 5th, big surprise, is also 0.000182. See how they're the same number? So you can do that to kind of make it a little bit easier for you to go, oh, 4.55 times 4 is equal to 18.2. Going 4.55 times 10 to the minus 5th to 1.8, you're like, I don't know. But when you get those exponents the same, that makes it much, much easier. And then you go, oh, well, 4 times 4 is 16. 4.5 times 4 is 18. So yeah, 18.2 sounds about right. So that means that if Cl2 is first order, then that means that NO is therefore second order. Okay, so we need an answer where Cl2 is first order, NO is second order. Again, let's just look at the explanation. It says because when the initial rate quadrupled, when NO is doubled, and doubled when Cl2 was also doubled. Okay, and that is exactly what happened. When NO was doubled, the rate quadrupled, and when Cl2 was doubled, the rate also doubled. That's a lot of words there. Okay, number 4. We saw a question like this already with the S208 in one of the videos we already watched. Okay, in the aqueous solution, the reaction represented by the balance equation above has experimental determined rate law. So we can see that S208, they're telling us, they're not asking us, they're telling us that S208 is first order, not because, again, of the balanced equation, but because of the rate law. If they give you the rate law, they're saying S208 is first order and I minus is first order because, again, they don't put any of the orders up in the corner there. So if the concentration of S208 is doubled while keeping I minus constant, which of the following experimental results is predicted based on the rate law and why? The rate will remain the same. Of course not. If S208 is doubled, of course the rate is also going to double. Okay, the rate of the reaction will double because the rate is directly proportional to S208 minus. I think that's right, but let's just check the other answers. The rate of the reaction will increase by a factor of 4. Again, no, has nothing to do with the balanced equation. And then the rate of the reaction will increase by a factor of 4 because the reaction is second order overall. Again, just because part of it's true doesn't mean the whole thing is true. Yes, of course, the reaction is second order overall, but it's not going to increase by a factor of 4. Okay, the rate is simply going to double. Okay, number 5. The rate of a certain chemical reaction between substances M and N obeys the rate law above. The reaction is first studied with M and N both, and again, here we can see they're giving us the rate law. So we know that M is first order, and we know that N is second order. Okay, so the reaction above, they're both 1 times 10 to the minus 3rd molar. In the new experiment, M and N are both 2 times 10 to the minus 3rd molar. How much will the rate increase by? Well, forget about the rate constant because that's not going to change. Unless the temperature changes, the rate constant doesn't change. We've already learned that, okay? And they don't mention temperature at all. So let's just figure it out. Forget the K part, but when you take 1 times 10 to the minus 3rd times 1 times 10 to the minus 3rd squared, Okay, what do you do with the exponents? First of all, here you multiply them. So that becomes 1 times 10 to the minus 6th. And then when we're not squaring them anymore. Now we're just multiplying them together. That becomes 1 times 10 to the negative 9th. Okay, when you do the same thing with 2 times 10 to the minus 3rd times 2 times 10 to the minus 3rd squared, then it becomes, again, 4 times 10 to the minus 6th. So this one here becomes 4 times 10 to the minus 6th. And this is obviously still 2 times 10 to the minus 3rd. 2 times 4 is 8 times 10 to the negative 9th. So it goes from 1 times 10 to the negative 9th to 8 times 10 to the negative 9th. And certainly when that happens, obviously that number is 8 times greater. So you're increasing by a factor of 8. So D is the correct response. Okay, number 6, the rate law is this. So you can see a lot of problems where they're just giving you the rate law, and you have to figure out how do things change when they change the concentrations. Okay, so NO2 is second order, Cl2 is first order. By what factor does the rate of the reaction change when the concentrations of NO and Cl2 are both doubled? Okay, and again, sometimes it's helpful. Forget about the rate constant again. Sometimes it's helpful just to put in real numbers. Let's say, and let's just use a really easy number. Let's use 2. Let's say the concentrations were 2. It'd be 2 squared times 2. 2 times 2 is 4. 4 times 2 equals 8. But now those numbers are doubled. And it doesn't matter the number that you use. You still will get the same answer. So if they're doubled, well, now it's 4 squared times 4. 4 squared is 16. 16 times 4 is 64. And again, you should see, let's say we use the number 3. 3 squared times 3, oops, that should be outside, is 27. And then if we double that, then it's 6 squared times 6. 6 squared is 36. 36 times 6 is 216. Duh. Okay, and obviously you can see here, how much is it going up by? It's going up by a factor of 8. 27 times 8 is 216. So no matter what, when those double, okay, you're going to go up by a factor of 8. And so what do you learn from that? Learn that sometimes it's easy when they don't give you numbers, just put in fake numbers. And then, then it's, again, no matter what number you use, you can see what's happening there in that problem. Okay, what is the experimental rate law for this reaction? So here we can see this is doubling, this stays the same, this doubles, therefore NO, again, I'm kind of moving a little bit faster now, is first order. Again, they try to trip you up by giving you the balanced equation to make you think, oh, NO is second order. Okay, and right now, hopefully it's really, really easy to go, no, you don't ever use the balanced equation. The problem is, months from now when you're taking the AP test, you're like, oh, do we use the coefficients of the balanced equation? Do we not? Okay, so hopefully you remember, don't use that balanced equation to figure that out. Okay, now let's look at, for O2, again, here NO is staying the same. O2 is going up by a factor of 4. What's NO2 doing? Again, make it easier on yourself. Move this decimal point one space over farther. That would be 80 times 10 to the minus 4th. So you're going from 5 to 80. Okay, and obviously 5 times what equals 80? It's 6. So you're going up by a factor of 16. So this goes up by a factor of 4. The rate's going up by a factor of 16. Again, 4, not times what, 4 raised to what power equals 16. Obviously, 4 raised to the second power. So O2 is second order. So NO is first and O2 is second. So NO is first and O2 is second. Therefore, the correct answer absolutely must be B. Okay. Question number 8. I think this is the last one. Again, lots of stuff going on here. Most of this doesn't reply to this question. Let's go to in an experiment, starting right here. In an experiment, a student studies. Sorry, I thought I shut that off. A student studies the kinetics of the reaction represented above and obtains the data shown in the following table. Use the data in the table to do the following. Determine the order with respect to S8. So here we can see the data table is down below, actually. So use the data in the table to do the following. So part 1 here says determine the order of the reaction with respect to S8, justify your answer. Now, this is one of those times when sometimes, like in real science, sometimes the numbers aren't perfect, and that's okay. Okay, you can't look at this and go, okay, OH minus stays the same, S8 goes up by a factor of 3, and then, oh, what does that go up by? Okay, it's not, in real science, the numbers aren't going to be perfect. Most of the examples you see, it will be, but like here, yeah, it's safe to say that's really close to 0.7, and 0.7 times 3 equals 2.1. So in this case, even though that's not exactly a factor of 3, it's close enough. And even here, 2.1 to 4.19, again, it's not exactly 4.20, but it's really, really close. And so you've got to be able to go, okay, that's close enough. So the order with respect to S8 absolutely is first order. How would I justify that? I would say in trials 1 and 2, again, OH minus stays the same. S8 increases by a factor of 3. So does the rate. Therefore, it's first order. You say it like that, that's a perfect answer on the AP test. Just, again, go through everything. Tell the trials. Say what's staying the same. Say what happens here, and then say what happens here, and then you're good. Okay, part 2 says determine the value of OH that was used in trial 3, considering that the reaction is first order with respect to OH minus. Justify your answer. Well, if OH minus is first order, and again, S8 doesn't change, and the rate does what? It doubles. If the rate doubled and it's first order, what must the concentration also do? The concentration is also just simply going to double. And again, how would you justify that? In trials 2 and 3, S8 remains the same. The rate doubles, and since OH minus is first order, it would also double. That's, again, just all that I'm doing is I'm just explaining the data that's already on there, just step by step. Talk about the trials, talk about what's staying the same, and in this case, talk about how the rate changes, and then therefore how the concentration of hydroxide will change. Okay, the next day, here we are back up here. We don't need that data table anymore. The next day, the student conducts trial 4, which again, not here, using the same concentrations of S8 and OH minus as in trial 1. So we're using these same numbers from trial 1, the 0.1 and the 0.01. Okay, but the reaction occurs at a much slower rate than in trial 1. And the student observes that the temperature in the lab is lower than it was the day before. So part F says using particle level reasoning, provide 2 explanations that help account for the fact that the reaction rate is slower in trial 4. So we know that when the temperature is lower, the rate constant is lower, but that's not what they're saying. They're saying use particle level reasoning. What's different at the particle level? Okay, because they knew that students were going to say, well, lower temperature means lower rate constant. You got to be really careful about how they want you to answer. Okay, so 2 explanations that help account for the fact that reaction rate is slower in trial 4 is, now go back, we got to go back to what are the things that make a reaction go faster or slower. One of them is temperature. Okay, at a lower temperature, they have a lower kinetic energy, which really still isn't quite at the particle level. We have to talk about the particles. Okay, but that kind of leads us into, at a lower kinetic energy, they are moving slower. Getting there, we're almost there. If they're moving slower, they hit each other. So they hit, I don't know what that is, hit each other less often. So there we go. Now we're talking about the particles. The particles hit each other less often, and what's the other one? With less force. That's what they're looking for in that answer. You're talking about the specific particles. What are they doing differently when you're at a lower temperature? They're moving slower. They're hitting each other not as often because they're not moving as fast. And when they do hit each other, they're moving slower. So that when they do hit each other, they're hitting each other with less force. Okay, and those are just some good example questions. Obviously, you can see these are straight from the College Board to kind of help you out with this section.